Welcome back to the lecture series on frequency domain analysis. We have completed one lecture dealing with the concept of frequency domain analysis, and this is the second lecture in this series. So, the learning objective for this lecture is to understand different frequency domain plots. So, in the first lecture, we understood that if I have an LTI system with the transfer function g of s, its gain for a sinusoidal input is given by g of j omega. In that case, if I give a sinusoidal input which is defined by a sine omega t, the output c of t is going to be a magnitude of g of j omega sine omega t plus phi, where phi is nothing but the angle of g of j omega. So what we notice here is when I send or when I give a sinusoidal input of frequency omega, the frequency of the output is also omega. There is no change in the frequency, but there are two changes happening at the output. One is at the magnitude and the other is at the phase. The magnitude, the input magnitude is multiplied by the magnitude of g of j omega, whereas the phase of the input signal is added with another angle which is given by angle of g of j omega. So we took an example, a first order system with a transfer function g of s given by 1 by s plus 1. G of j omega we can obtain for that system as 1 by j omega plus 1, that is obtained just by replacing the s term by j omega. So this will get reduced to a complex number. As a complex number, it will have a magnitude and also an angle. The magnitude is given by 1 by root of omega square plus 1, and angle is given by minus tan inverse of omega. So if I send a signal, if I give a sinusoidal signal as an input to this system, I will have another sinusoidal signal at the output. Only thing is the magnitude will get changed with an addition of phase angle. With this discussion, we came to the conclusion that to understand the behavior of a system, an LTI system for a sinusoidal input, it is sufficient to understand the variation in the magnitude of the g of j omega and the angle of g of j omega with respect to the frequency. So this made me to plot two plots. One we call as the magnitude plot and the other one we call as the phase plot. We plotted the magnitude of the system, that is magnitude of g of j omega with respect to frequency, and angle of g of j omega with respect to frequency. This plot is what we called as the frequency response. So this is the first frequency response plot we are going to look at. So here the magnitude and the phase are plotted with respect to frequency on a linear scale. Both the angle and frequency are on the linear scale, and similarly the magnitude and frequency are also on the linear scale. The magnitude plot is redrawn here, and you can notice that the magnitude plot is drawn for a frequency range from 0 to 100 radians per second, and we are able to see that at lower frequency up to maybe 10 radians per second not even up to 10 radians per second, maybe around 1 or 2 radians per second, the gain is almost close to 1, and then it decreases sharply. And when the frequency is around 40 radians per second, the gain has almost become 0. So this is what we infer from this magnitude plot. Now, I'm going to increase this frequency range. I'm going to plot the same frequency response for an increased frequency range. See what happened? That frequency range has been increased from 100 to 200. And if you compare these two diagrams, the low frequency part where there is some change that I could notice is shrinking when I increase the frequency range. What if I increase the frequency range from 200 to 500? Again, you see the variation at the low frequency range I am not able to visualize. What if I increase the frequency further to 1000 radians per second? Then again, so almost I'm not able to see visualize the variation in the gain at the low frequency range. So this is the problem. So how can I overcome it? So rather than taking the x-axis or the frequency axis in linear scale, what I can do is I can take the frequency on a logarithmic scale. In logarithmic scale, each division is marked as 10 power n, where n is an integer. The starting and the ending values depends on the frequency range in which I am interested in. I have taken the starting frequency as 0.01 or 10 power minus 2. In that case, the markings go as 0.1 or 10 power minus 1, then 1 or 10 power 0, or 10 or 10 power 1, or 100 or 10 power 2, 1000 or 10 power 3, 10,000 or 10 power 4, and so on. I can even take the starting value as 0.001, or that is 10 power minus 3 also. In that case, the first value will be 10 power minus 3 and 10 power minus 2, 10 power minus 1, 10 power 0, 10, and it goes on. And with this scaling, the advantage is I'm able to have a wide range of frequencies. I'm able to take a wide range of frequency from 0.01 to 10 power 5 radians per second, but at the same time not compromising on the low frequency variation. See, in the previous plot where the frequency was taken on a linear scale, the low frequency variations were not visible even with the frequency range of 0 to 1000. But when I change the scale to logarithmic scale, so I'm able to visualize completely the low frequency variations. But at the same time, I'm able to accommodate a larger frequency range. This is the advantage of using the frequency in a logarithmic scale. This is the magnitude versus log omega plot, and this is the second plot for representing the frequency response. And at this point, it is worthwhile to note how the concept of frequency response or the frequency domain analysis evolved. One Mr. Hendrik Bode, while he was working in Bell Laboratories of USA in 1930, noticed that the electronic circuits such as amplifiers and oscillators, which were tested good in time domain behaved strangely for some frequencies of input signal. It made him to explore the performance of the system with respect to frequency variation. And this resulted in the frequency response plots. Since this work started with analyzing oscillators and amplifiers dealing with sound signals, the gain was plotted in decibels because the ear responds to loudness of sound logarithmically in decibel scale. Gain in decibels is obtained by taking the log of g of j omega to the base 10 and multiplying it by 20. Otherwise, this g of j omega, the magnitude of j omega, I can convert it to decibels by taking 20 log of g of j omega, that is magnitude of g of j omega. That will convert this magnitude or the gain to decibels. This is Henry Bode, and by his method, we have changed the gain axis or the vertical axis into decibels, 20 log 10 of the modulus of g of j omega. Though this practice of converting the gain to decibels was followed for amplifiers and uh, oscillators, the same practice is followed for other systems also, even for electrical, mechanical, or electromechanical systems, because converting the gain into decibels has got some advantages both analytically and in understanding the systems, which we will be seeing later. We still continue the practice of converting the gain to decibels. So therefore, as proposed by Bode, we take the frequency in the horizontal axis in logarithmic scale and we convert the gain to decibels and we take that decibels value in the vertical axis on a linear scale. Please note that though the gain is converted to decibels, the scale is going to be linear, whereas the frequency will be a logarithmic scale. Such a plot in which the magnitude in decibels is plotted against omega or the frequency in logarithmic scale is called the Bode magnitude plot. So this is the Bode magnitude plot. Let us see how these values, how these gains changed Let us see the gain before and after changing or converting into decibels. Before converting into decibels, the value varied from 0 to 1. The maximum value was 1, and then as frequency increased, the gain reduced from 1 to 0. So when I changed to decibels, the 1 was converted to 0 decibels because log 1 to the base 10 is 0. So therefore, 0 decibels means the gain is 1. What do you mean by the gain 1? Whatever input I give at the input will be appearing at the output. Otherwise, the magnitude of the input, amplitude of the input, and the output is same. That is what is meant by 0 decibels. What do these negative decibel values mean? Whenever the gain is lesser than 1, when it is converted to decibels, the decibel value becomes negative. Also, please note that this minus 20 corresponds to a gain of 0.1, minus 40 corresponds to a gain of 0.01, and minus 60 corresponds to a gain of 0.001. This you can verify. And if the gain is more than 1, when it is converted to decibels, the decibel value will be positive, and a decibel value of 20 plus 20 signifies that the gain is 10, and a decibel value of plus 40 signifies that the gain is going to be 100 or 10 square. So this understanding is necessary. Anyhow, so plotting this magnitude converted to decibels against the frequency in logarithmic scale, we call it as the Bode magnitude plot. So therefore, so far we discussed only about the magnitude. When it comes to the phase, again, the phase angle in degrees is plotted against the frequency in a logarithmic scale. So this plot, we will be calling it as Bode phase plot. Please note again, in Bode phase plot, we take the angle of the system, angle of G of j omega in degrees, and we plot it against the frequency on a logarithmic scale. This Bode magnitude plot and the Bode phase plot together, we simply call it as Bode plot. This Bode plot corresponds to the first order system which we took, that is whose transfer function is given by g of s is equal to 1 by s plus 1. And what we notice here is up to a frequency of 1 radians per second, the gain is 0 decibels, which means that the gain is almost unity. And after 1 radians per second, the gain reduces. For example, this is at 10 power 5, frequency of 10 power 5, the gain is almost minus 100, which means that the gain is 10 power minus 5. So it is a very, very small gain. And also, when you look at the phase plot, what we understand is at lower frequencies, the phase shift introduced into the signal, input signal, will be very, very small. But as the frequency increases at around 1 radians per second, the phase shift that will be introduced will be 45 degree or minus 45 degree. Minus 45 degree means that the output will be lagging the input by 45 degree. So that means the system introduces a phase lag of minus 45 degree. And as the frequency increases further, the phase shift introduced increases, and at last, as the frequency increases to a very high value, the phase shift introduces becomes almost 90 degree. So this is what we read from this Bode plot. So this is the third plot, that is the magnitude in decibels and the phase angle plotted against the frequency in on a logarithmic scale. Fourth plot, very widely used in control systems, is the polar plot. Let us try to understand what is this polar plot. Let us consider the system again, the same system whose transfer function is given by g of s is equal to s plus 1, a simple first order system. and g of j omega is going to be 1 by j omega plus 1, and let us calculate g of j omega for a frequency of 0 radians per second. In that case, I'll just put omega is equal to 0, then it becomes 1 by 1, that is equal to 1, or in complex form I can write it as 1 plus j0. Anyhow, I can say that I get a complex number for a frequency omega is equal to 0. This complex number I can represent in a complex plane as a phasor. How do I represent? The real value is 1, and therefore on the real axis I have to take 1, and at the imaginary axis it has to be 0, so I need not move. So this is the point. So this is the point which represents 1 plus j0. So I can draw a phasor like this. So this phasor represents this complex number. Again, the same complex number can be represented in polar form also. If it is represented in polar form, the magnitude is going to be 1 and the angle is 0. Anyhow, the phasor's magnitude will be 1 and the angle is 0 because the angle is measured from the real axis as the reference. Now, let me increase the frequency from 0 to 0.3 radians per second. So omega is equal to 0.3. When I did, I get this complex number. If I simplify, this is what I will get. So again, I can represent this complex number on a complex plane. Please note that this is the real axis and this is the vertical axis is the imaginary axis. So this complex number has got a real part of 0.9174 somewhere here, and the imaginary part is minus 0.2752, minus 0.2752. Okay, so therefore this is the point and I can draw the phasor. Again, if it is converted to polar form, the magnitude is going to be 0.9578 and the angle is minus 16.69. Since it is a negative angle, it has to be taken on the clockwise direction. So it means that this angle will be minus 19.69 degree and the magnitude is 0.9578. What if I increase the frequency from 0.3 to 0.5 radians per second? You'll be able to see that this is the new value, and this new value, if plotted, this is what I get, this is the phasor I get, and the value converted to polar form will result in this, and the angle has increased whereas the magnitude has reduced. So I increase it further from 0.5 to 1 radians per second. The magnitude reduced, but the angle increased. Angle in the negative direction increased. So increase further, the rate I made the uh, frequency from 1 radians per second to 3 radians per second. Again, the magnitude reduced from magnitude reduced from 0.707 to 0.3162, whereas the angle increased from minus 45 degree to minus 71.54 degree. And this is what is the Cartesian coordinates or rectangular coordinates for the complex number. So I'm increasing the frequency further, making it as 5 radians per second. Again, the magnitude is reduced and the angle increased. So for 10 radians per second, it is very small and the angle increased. I made it as 50 radians per second. You can see that the magnitude is only 0.02 and the angle is almost going close to minus 90 degree, 88.9 degree. So I increase the frequency to 1000 radians per second. The magnitude is 0.001, whereas the angle is minus 89, almost 90 degrees. It is a very, very small phasor. Okay. So see how the phasors moved from the real axis to the origin when I increase the frequency from 0 to 1000 radians per second. See that. So this is for 0, increased, frequency increased, the phasor rotates and comes to 0. Okay, so this is how the phasors moved as I increase the frequency. So when the phasors moved in this way, in the clockwise direction, the end of the phasors traced a curve. This curve is what we call it as the polar plot. Locus of the gain phasors in the complex plane for different frequencies is what we call it as the polar plot. So this is the polar plot removing the phasors. So you need not draw the phasors every time. Only the endpoint you can plot and you can connect those endpoints to get the polar plot. Please note, this polar plot is drawn on an ordinary graph sheet. However, this polar plot can be plotted on a polar graph also. This is what is a polar graph. Let me explain a little bit about this polar graph. See, the polar graph has got many equidistant circles, and equidistant and concentric circles having the same center. Each circle represents some magnitude. For example, this circle represents a magnitude of 0.2, whereas this circle represents a magnitude of 0.4. And this circle is 0.6 and this circle represents 0.8 and this one 1. And it has got some radial lines also. So this line, the horizontal line, is usually taken as the reference, and these radial lines are used to mark the angles. So the radial lines will have equal angles between them. In the given polar graph, the angle between each division is 30 degree, but in the market there are polar graphs with 15 degree markings or 10 degree markings. So we can make use of this angle markings and the magnitude markings. We can represent the phasors on this polar graph. One more thing to be noted is the angles are positive, or it will be increasing from 0 to a positive value in the anti-clockwise direction, and in the clockwise direction it will be negative. For example, this is 0, this is plus 30, whereas this is 0 and this will be either plus 330 degree or minus 30 degree, and similarly this will be minus 60 degree and this will be minus 90 degree and so on. In the polar graphs which are available in the market, you will be able to see both the markings, both positive and negative angles, or you can mark the angles. And for a frequency omega is equal to 0 radians per second, the complex value was 1 angle 0. So how do I mark it? First, identify the angle. Angle is 0 here, and therefore this is the reference angle, and this point is going to lie on this line. And what is the magnitude? It is 1. So in this line, find out the circle which represents a magnitude of 1. So this is the point. And then the next phasor for a next frequency is this. So I think this is for a frequency of 0.3 radians per second. We got this complex value in polar form. So first thing is you have to look at an angle of minus 16.69 degrees. So minus 16.69 degree you have to take. You have to identify the line which is for minus 16.7 degree. And in that line you have to take a magnitude of 0.9578. So in this way you can draw all the phasors and you can connect the ends of all the phasors. So a polar plot can be drawn either on an ordinary graph or on a polar graph. Where irrespective of the graph on which it is plotted, it is called as the polar graph. This is the polar graph, okay, without the phasors. So here there is something written. So it shows in which direction the frequency increases. For example, when the frequency was 0, so the point was here. When the frequency increased a little bit from 0 to 0.3, the point moved here. And so this is the direction of increase in the frequency. So the major difference between the Bode plot and the polar plot is, in Bode plot, you'll be able to see the frequency explicitly, whereas in polar plot, you cannot have the frequency details explicitly. And in Bode plot, you take the magnitude in decibels, whereas in polar plot, you don't convert it to decibels, you take the gain as it is, g of j omega as it is. Okay, so in Bode plot, you take the magnitude and the phase angle separately, whereas in polar plot, you take them together and represent it as a phasor which contains both magnitude and angle. These are the major differences between Bode plot and the polar plot. This polar plot is also a very important tool in the analysis, especially by looking at the shape of this polar plot, you can find out the order and the type of the system. So therefore, we have completed the fourth plot which is used in frequency response or frequency domain analysis. There is another way of representing this frequency response also. Why not I take this magnitude in decibels and the phase angle in two different axes? This is another way. I take the magnitude in decibels in the vertical axis and the phase angle in degrees in the horizontal axis. This is how it goes. Okay, right. So you will be able to see that this is the plot corresponding to the system we took. That's a first order system, the transfer function 1 by s plus 1. So you notice that at a frequency of 0, the magnitude was 1, and when it got converted to decibels, the magnitude is 0. So this is the point, and the angle is 0. And when the frequency was increased, the magnitude got reduced from 1. So when it got converted to the decibels, you get negative values, and negative value increases because the gain reduces to a very small value, and at the same time you'll be able to see that the angle increases in the negative direction from 0 to 90 degree. This is almost 90 degree. Okay, please note I have specifically written here as open loop phase angle. Usually this particular plot, that is magnitude in decibels versus phase angle, is plotted on a chart. This is a chart. This chart we call as the Nyquist chart. Nyquist chart contains many circles. They are M circles and N circles. We'll study them later. So when this plot for an open loop system, when this plot is plotted for open loop gain, using this chart, I can find the gain for a closed loop system by using some graphical methods. That is the advantage of this Nyquist chart. So that is why I have specifically used this open loop phase angle here. So this is the fifth type of plot in frequency response or frequency domain analysis. So here the magnitude in decibels is plotted against phase in degrees. So altogether, we have studied 5 plots. The first plot was very ordinary plot, like both magnitude and phase angle were taken on linear scale. Okay, it was on the linear frequency scale, and the next plot, the magnitude and phase were drawn on log omega scale, log omega axis. And the third plot is the Bode plot. It contained both magnitude plot and the phase plot. And this magnitude plot, in the magnitude plot, the magnitude was taken in decibels and the frequency was taken in a logarithmic scale, and phase was taken in degrees, and it had two subplots. The Bode plot has got two subplots, Bode magnitude plot and Bode phase plot. And this Bode plot is drawn on a semi-log graph because only one axis has got a logarithmic scale. That is why we call it as a semi-log graph. The next plot what we took was the polar plot. So in that the magnitude and phase angle were taken together as a phasor, and the phasors were drawn on an ordinary or a polar graph, and the curve traced by the ends of the phasor is what we call as the polar plot. The last plot is the magnitude in decibels versus phase, and it is drawn on a Nyquist chart, and which is very useful to calculate the closed loop gain from the open loop gain. So out of these 5 plots, these are all the 3 important plots, that is the Bode plot, polar plot and Nyquist chart. Mostly in this frequency domain analysis, we will be dealing with these plots, and we will study about these plots in detail in the forthcoming lectures. With this, we will close this lecture. Thank you for watching.